Right. All right, so welcome everyone to the set theory seminar. We have today a second lecture by Andrés Villaveces from the National University of Bogota at Colombia. And he will continue speaking about two logics and their connections with large cardinals. And I'm very excited because we will get some large cardinals today, according to Andrés. Andrés, go right ahead.
Okay, thank you very much. Thank you so much, everybody, for being here again. Those of you who are for a second time, and thanks, of course, to Vika for the original invitation. Again, this prompted many things. Now, last time the lecture was about the two logics, and really, well, there were no large cardinals nor anything and like that. It was a plain description of some of the properties of these two logics. Today, I want to give the connections with large cardinals, but I plan to start by giving a quick review of the two logics. So this was the last slide last time, and let me just make this slightly small. Okay, yeah, this is better, I think. Okay, so yeah. So now, in our session 2, this will be a little bit different. So if you look, the planned session in session 1 only had 3 parts, SHELAH's logic and Cartagena logic and basic properties that were dealt with in detail. Now we have a lot of things, but they're very short. So this will be a more kind of an impressionistic overview of some ideas that some of you might recognize and that some of them might be new. Of course, with 8 steps to the game today, you can expect that each one of these steps would be like a very short piece. So yeah, it's like last time it was more like maybe like a sonata structure. Now we have these scores, and today it will be hopefully divertimento, hopefully like bagatelle. Maybe many things will be perhaps more, well, not superficial in a bad sense, I hope, but less developed and more kind of hinting at possible connections, because these are questions for the authors of the paper, and I want to describe a little bit of what's going on and why I ask these questions. So today we have the connections with large cardinals and forcings. I will start by the review of the 2 games, and then we'll go through virtual large cardinals, virtuality and fourth games, some characterizations of compactness, virtualization of a logic, L1 theta, which would be the same as L1 kappa, but when theta is a strongly compact cardinal, the virtualization of these logics, new cardinals, delayable and virtually delayable cardinals, and finally some musings on pseudo-models, forcing and saturation. Okay. So remember, we are in this area in the map of logics, kind of L1 kappa is at the center, and we had this approximation that we saw last time. I don't know why this is, anyway, let me try something. Okay, yes, okay, yeah, good. So recall the SHELAH logic game. So I just recall the picture of the logic game. Maybe it is good to know that the red moves are the challenger moves, or the bad moves, or the anti-isomorphism moves, and the green ones are the isomorphism moves. And I just recall that, so the first player chooses an ordinal, it is going down, it's beta 0 less than beta. Then a challenge that I put here on the left. Then the response is break up the challenge into omega many parts and respond in the first stage of the game, just to the first part. So somehow the isomorphism player has a shot at delaying difficulties. Now, next challenge is, okay, so the clock is going down, so beta 1 is less than beta 0. New challenge, A1. The isomorphism player can split the A1, she splits it into omega many pieces again, and now she has to respond to the first piece of the second challenge and to the second piece of the first challenge in a coherent way. And then it goes on like this. So the ordinal goes down, new challenge, new split, and so on. And let me just, this is a summary of the first part of last lecture. So we have a game, and we can declare the 2 structures are isomorphic for the game, or equivalent for the game, if the isomorphism, the constructive player, has a winning strategy. That's the first verb. that was not necessarily transitive. So we define elementary equivalence in the logic as the transitive closure of that relation. And then we call a sentence a union of that number, up to beta plus 1 of theta, where theta is just some cardinal below, the kappa, the main parameter of the logic, equivalence classes. And that's a sentence. Now, this is something that's, also for first order, it happens, and it is equivalent to be in a sentence in first order, but that's just, some side remark. The logic turned out to be in between L lambda plus omega and L lambda plus lambda plus. So those very, well-known logics were kind of upper bounds and lower bounds. Then it had a very an extremely important property for technical reasons and reasons that make it connected also with abstract elementary classes, closure under unions of omega chains. Now, unfortunately, here we have the demand here that the chains are in a stronger logic. So there is something weird. If you have moles of a sentence, each one of them, and you have a strong chain, then the limit is also a mole of that sentence. Then Craig interpolation is true for that logic, and that was the original motivation I gave last time. And we also got, with more work, some strong form of indefinability of will order. So it's kind of the remnant of compactness that we get for this logic. And even a Lindstrom theorem when kappa is a strong limit of cofinality omega. So this summarizes a lot of things that we saw last time. Hopefully, for those of you who were here a week ago, the picture will remind you of something. I think the dynamics of the picture is important. It's nice. It's interesting. There is a delay, and the properties. Of course, you can imagine that one has to build strategies, adapt strategies, combine strategies for the ISO player and or for the comparisons with other logics. Bad thing about this logic is that sentences are these weird objects. So there was this. From our joint work with Jouko Väänänen, Cartagena logic, L1C kappa, it is similar, but now we built it from L kappa omega by means of the two constructions. So we have these two basic constructs, which are a universal, long universal up to theta, and then disjunction over functions from theta into n. And then, the conjunction in the first one is an omega conjunction, and then some formulas, and the dual construct. And you close it, and there are these operations plus the usual operations. So this clearly, I mean, by the syntactic description, this is clearly a fragment of L kappa kappa, and well, it is built on L kappa omega, so it is also in that same region. But of course, it could be totally different from the other logic. However, it can express a lot of things like cardinality quantifiers, existence of long descending chains. It can also, it's nice to also have a game, because then the Cartagena game, which I put the picture here, we described it last time, it's also, it allows to compare in a kind of nice way with the SHELAH game. The picture is almost the same. So remember the picture of the SHELAH game, there is the delays and the splitting. And here you also have the splitting, but instead of going, like paying the delays in order according to the splitting, the challenger has a chance to choose which piece is going to be responded to, but then that's the only piece that the isomorphism player has to respond. So it is slightly different, and of course, in the details of the comparison, there are lots of devilish situations that may happen. Now, let me just mention that things like Arnstein trees or Suslin trees or Suslinity or tree properties more in general are very much adapted to a sort of thing that can be captured with these logics and cannot be captured normally with like a first order or even L omega 1 omega. So these logics see a lot of properties, combinatorial properties of objects like trees and also more theoretic items that are important, like combinatorial set theoretical items that are important in model theory. This also has closure under unions of omega chains from a different argument, and just elementary in this logic. So it has a better closure property than the SHELAH logic, I would say. So it has good things, better syntax, better closure properties, and bad things. The bad thing is it doesn't have interpolation. It doesn't have a Lindstrom theorem. However, it does have Lowenheim-Skolem, weak versions of Lowenheim-Skolem theorems. Of course, it will have undefinability of well order, but that's, well, of course, once you compare it with the SHELAH logic, since it is weaker than the SHELAH logic, of course, if the larger logic cannot define well order, the smaller logic will not be able to do that either. But the connection between the two logics is this delta operator that I defined last time. That is, the delta closure of this logic, of this nice logic, is the SHELAH logic. And so really the theorem is that delta of this contains any logic that satisfies the union lemma for elementary chains in theta L theta plus. And SHELAH was, SHELAH's logic had the property because of some comparison that he had. Okay, so far so good. So we have these two. This is the review of last time. Very quick review. I hope it makes some sense. We will come back to these logics, but now we completely, we start our new stuff here, speaking a little bit about virtually large cardinals first, and some of the topics that I, promised in the first slide. So the history of virtually large is there are large cardinals, but there is some virtuality built in, and the virtuality is kind of added by the presence of, the witness of the largeness of the cardinals is not really in the universe, but it will be in some forcing extension of the universe. And one could say, well, it's a nice variant, but it turns out it has a very beautiful history. Schindler, around 2000, he first was studying something called remarkable cardinals, and he proved that these are equiconsistent with the fact that the theory of L of R cannot be changed by proper forcing. So at that time, this was, I think, a major, connection between some large cardinal property and some robustness of the theory of L of R. For reasons that had to do with descriptive set theory, this was important. This was important also as part, as a kind of input into some larger scale program that I don't know much about. I know about, but not in detail. But these remarkable cardinals were defined in a quite complicated way. If you look at the original definition, it looks quite scary. However, it is nice to know that these remarkable cardinals are quite low in the large cardinal hierarchy. So later, the original complicated definition of remarkability was proved by Schindler to be equivalent to being virtually supercompact. So supercompact is a notion that I would say everybody knows, or everybody in this, this sort of seminar knows, or I mean, it is certainly not a scary definition in the way the original definition of remarkable cardinals was. And then knowing that that important definition, once you apply the adverb virtually, gives you this, tells you, well, there is something going on there that I think is interesting. Perhaps, way beyond what my own scope, what I can say in this lecture. Of course, I will just give the idea. There are many absoluteness details that are tricky in this sort of ideas, as you can imagine. But the idea is that a large cardinal that is defined by properties of an elementary embedding, like measurable cardinal, like supercompact cardinal, can be virtualized by requiring the embedding to exist in a set forcing extension of V. This is, I'm kind of putting some details under the rug here in some sense, but this is somehow the idea. And the important thing is that virtualized large cardinals are still large cardinals in the sense that they are outside of ZFC, but they're much smaller. It's much easier to be a virtual version of a large cardinal because the extension doesn't have to live in the universe, but it may just live in some set forcing extension. And it's interesting that these are still large cardinals, but they are now in the neighborhood of so-called omega Erdos cardinals. They're kind of they're ineffable. They're kind of low, and they are consistent with L. So it's a whole world of small, large cardinals that somehow have some kind of reflection property that makes them similar to large cardinals. I've been fascinated with that sort of a connection ever since my PhD thesis that introduced some other kind of small cardinals, small large cardinals, about which I would just ask one question at some point here. The strongly unfoldable cardinals that have been studied by people in the New York logic seminar. So the question is, strongly unfoldable, a virtual cardinal notion. I don't know about, maybe Vika would know, or maybe somebody else would know. I don't know if it is the virtualization of something. I have the impression that they are very close to remarkable cardinals, but there are some subtle details about expansions and things. I just would like to know. So this is my first question for Vika, perhaps, or for people who know about virtual large cardinals. This is just out of pure curiosity. I have no additional further motivation to this. That I introduced these strongly unfoldable cardinals many years ago, when looking at questions inspired by Enayat's analysis of models of arithmetic and trying to transfer some of Enayat's analysis to models of set theory, which are much harder even than models of arithmetic. And somehow, at some point, the notion of strongly unfoldable cardinals, also unfoldable and strongly unfoldable, appeared. At first it was like a purely like an Enayat like the sort of thing that people, or like Roman Cossack or Schmerl, would be interested in, and then it became slowly a kind of more traditional large cardinal hypothesis, and many people, including myself, proved undestructibility properties of those cardinals, and so on. Okay, so a cardinal kappa is virtually super compact. Just to remind you of some definitions, or remarkable, if for every lambda above kappa, there is alpha above lambda, and the transitive M, the transitive model M, that is closed under lambda sequences, such that there is a virtual elementary embedding J from V alpha. This, it's usually from V, but it can be, you want to have a set version of this for technical reasons. So from the set V alpha into M with critical point kappa and mapping kappa above lambda. So the only new thing with respect to supercompact is that we now have the virtual here. So it is no longer, there is an elementary embedding, but there is a virtual elementary embedding. So similarly, so in the paper by Dimopoulos, and then the paper by the four authors, I will mention more in detail the paper in a moment. There are also virtually Wooden, virtually extendable, virtually measurable, and many of them have been characterized in ways that are what I want to describe today in connection to our new logics. In particular, there is this other definition that is kind of similar to virtually super compact. So it is also virtually something, and now it is virtually extendable. If for every, so kappa is virtually extendable if for every alpha above kappa, I think, yeah, there is no lambda, sorry. So this should be a kappa. There is a virtual elementary embedding. Now, the domain is V alpha, again, like before, into some V beta, and that's very, very different from just saying that we have seen here some M. It is really into some V beta, so it is much more difficult to get such a target of the elementary embedding. And again, with critical point of J is equal to kappa and mapping kappa above alpha. So it is kind of very similar. The main difference is the sort of target. This one here will not just be closed under lambda sequences, but it will be a whole layer, or a whole stratum of the hierarchy, of the cumulative hierarchy. Now, let us look a little bit at the strong compactness cardinal of a logic, and let's go back in time a lot. Okay, it's embarrassing. 50 years. So in 71, Magidor proved that extendable cardinals. So extendable cardinals are like the virtually extendables we had in a moment ago, but with the embedding in the universe. They are so-called strong compactness cardinals for second-order infinitary logic, L2 kappa kappa. So it's second order plus conjunctions, disjunctions, kappa kappa. So you see, you can sense a little bit where I may be driving all this discussion to. And this means being, a strong compactness cardinal for a logic means that for every less than kappa satisfiable theory in this logic, that theory is satisfiable. So this opened up a line of many connections between being, being a strong compactness cardinal, or maybe there are also variants of the kind of compactness property we want, and then, well, that turned out to be connected with the sort of logic you are looking at. So this is one of the first items here. So in a way, it is quite natural, because you're looking at logics where you want to have some kind of compactness properties, but they happen if the parameter of the logic, or the parameters here, kappa and kappa, are in themselves large enough cardinals. This wouldn't happen, like for L omega 1 omega or something like that. And this prompted many questions. So in the recent model theoretic characterizations of large cardinals, I don't know if, has it, I think it is still in a preprint form of, but is that the case, Vika? Or
yes, yeah,
okay.
I have an updated draft, but it's still, I am waiting on my co-authors to.
Okay, because I wanted to put here like 2020 or 2021, and then I realized that, yeah, it is still, there's something very interesting going on there. And I will try to convey why I find it interesting, which may not exactly, not be exactly the same reason why the four authors find that work interesting. But this is the spirit of this second lecture, kind of pointing in some directions. So they first of all generalize Magidor's early result to virtually extendable cardinals. So now you have much smaller cardinals, but there is a virtual thing. So now what is going on? Before we had that the extendable cardinals were the strong compactness cardinals for some logic, L2 kappa kappa. Now we want to change the cardinality, have to go down. Of course, we cannot expect to have them being strong compactness cardinals, but maybe they still capture some form of compactness that is still there. You can imagine that I am interested in weak forms of compactness for reasons that have to do also with my own work in abstract elementary classes, where we don't have compactness, but we do have consequences of, for instance, undefinability of well order, essentially in the class. So one of the theorems is that kappa, cardinal, is virtually extendable if and only if every less than kappa satisfiable L2 kappa kappa theory has, well, I would like to say has a model, but that would be being, the strong compactness cardinal, and these are much smaller, but it has a pseudo model. So what is a pseudo model? Well, they introduce what they call the filtering of being a model. Let me just check if battery, I still have battery. So they introduce a kind of being a model of something, but in a filtered way, or in a kind of maybe localized way that I will discuss in a moment. So they change being a model of a theory to being a pseudo model of a theory, and then they get the equivalence with the virtuality of the cardinal. And I was intrigued by this. So let me try to say a little bit of what are these filtered models. You will excuse me, Vika, if my description will sound, like preposterous to use, as you are one of the authors of this. But I want to engage this because it looks similar to other definitions I have seen. And okay, so here's the definition. There'll be a picture in a moment. But let's go over the definition. So there is a Tau theory. So you have a vocabulary, Tau, and you have your theory that you are, want to somehow understand. And there is some Tau star structure. So this is a kind of strange beginning. when you have a tau theory and a tau star structure. Well, that's exactly the point. You don't want to have directly the structure to be, in the same vocabulary, or not necessarily. You allow yourself the freedom of doing translations. Now, of course, there are many kind of translations. You could do interpretation. You could do, there are many situations where one can say, well, I have a theory. I cannot give you a model in this, direct vocabulary because, things are more difficult. I don't have, I'm not with large cardinals, or I don't have enough compactness or saturation or whatever. But I can, if I change a little bit the vocabulary in a nice way, I can give you a model, and you will have to live with that. And this is a little bit what's happening here. So this happens through a fourth system, F, from the first vocabulary to the second vocabulary, and that's just a collection of renamings. And here the renamings are functions that go from finite subsets of the first vocabulary into finite subsets of the second vocabulary. So when you have star, you're in the second vocabulary. When there is no star, it's the original one. So you have renamings F from sigma to sigma star, where these are finite subsets. I put here finite. Of course, there are versions of this where you bound the cardinality, but let us stick with finite for a moment, in such a way that, first of all, the empty set is part of your system. And if you have a function in the system and you have any finite subset of the original vocabulary, there is some function in the system that extends the function F you started with, and that captures the domain, whose domain, captures that extension, that finite subset of the vocabulary. So it is really like in the back and forth systems that we are so used to in all logic, I would say, except you don't have it back. There is no symmetry here. It is only going in one direction. Fine. I mean, it is quite natural in some sense. Of course, you won't be able to, like simulate isomorphism or anything. You will only be able to simulate what? Well, essentially elementary embedding, and that's nice. So M is a pseudo model of T or for T. I think they use for T in the paper. I'd say of T of the theory. If there is a fourth system, like a way to translate in a way that has the extension property, such that for every F in F, M satisfies the direct image of the theory, but restricted to the domain of F. That looks a little bit, but let's just say, well, the domain of F, remember, is some finite set. So the theory might only have, some symbols. So you just look at the theory on those symbols, and then you map it, and then you say, well, M is a model on that side. So maybe it should be M star because it's on the star side. Now there is a picture here. So the picture is on the right. You have tau and tau star, the system. You have sigma and sigma star, small subsets, finite. Then you have your theory, for which you're somehow trying to get a model. But then you don't get a model of T, but you get what they call a filtered model or something like that, where anytime you take a small piece of the theory, and that's what they call T to the domain of F that is attached to sigma. So to sigma in the vocabulary, I attach in a natural way, like the sigma part of the theory. And then I have the map induced by some F from sigma to sigma star. I forgot to put here F from sigma to sigma star, or in this case, it'll be F. Then that transforms, you transform the vocabulary, the map extends to formulas in the theory, and then you get something here that is in tau star. And then you say, oh, M was really a model in the usual sense of this. But if you take another piece, oh, you get another piece here, and M is also a model of that. So it's like transferring you could say, well, you're not doing much because, I mean, the whole point of compactness was you had models of small pieces, and yes, but the translation might actually give you a lot of power into blending all these pieces. And well, normally you won't get a model for the whole of T, but you will get something better than just having pieces of T of the models. I just copied the definition of the pseudo model here because I have some properties here. So you can look at the picture and you can look at the definition, and then let me just say a few things about this that are pure musings. There is nothing, there is no theorem in this slide. It's just general observations on this. So the notion of a pseudo model deals with localizing in coherent ways, like a sheaf-like construction, the notion of being a model, through fourth systems between vocabularies, as we saw, that are connected with forcing notions whose generic would precisely be a bijection from tau into tau star. And from this bijection, one constructs actually embeddings in the, in the forcing extension from V alpha to V beta. I'm not saying what they are. This, takes a significant proof in their paper. But the whole point is that all of this may be encoded in a correct theory in the second order logic kappa. And it is worth mentioning, perhaps for people who worry about the second order part of this, I know that John might be asking that question, where do you use the second order part? And it is essentially to say that the model looks like a V alpha because of some trick that Magidor had invented, a long time ago. It's called the phi sentence of Magidor. It's a second order sentence, but other than that, there are many parts that are first order infinitary that deal with, encoding in a nice way. The other direction, so remember the two directions are you're virtually extendable if and only if your, every satisfiable L2 kappa kappa theory has a pseudo model, and the other direction uses the virtual embedding. So if you have the virtual embeddings, if you're already virtually extendable, then you actually can extract from the embedding the fourth system. That's a natural but a nice thing to see. I just want to describe it here. So what you have is you weaken the notion of a model, and then things will happen in the forcing extension. So the motto here is that fourth systems between vocabularies somehow correspond to forcing notions that will bear witness for the virtuality of the cardinal. This is an oversimplified motto. If you look at the paper, you know that there is much more subtleness behind this. But I like this idea, and I think it is powerful to kind of think of fourth systems in two ways, as forcing notions for virtuality on the one hand, and as, well, if you're interested in elementary embeddings, like for instance, if you're looking at abstract elementary classes where elementary embeddings are the meat and potatoes, so to speak, at least in part of them, even before having a theory, well, fourth systems are good ways of dealing with approximations of those embeddings. So back and forth systems are good approximations of, weak versions of isomorphism. Fourth systems would then correspond to weak approximations of embeddings. So this is the first picture I wanted to share with you. Just, put the picture in larger so that you can kind of, the pseudo model is really following all of this. There is also something called the virtualization of a logic. It is a related notion, but it has a lot of similarity, but it is different. So now we can also think of using fourth systems for models and not for vocabularies as above. So in the picture here, the fourth system F here was going from a vocabulary to another vocabulary, and doing all this kind of syntactic transfer from theory, or the theory restricted to some sigma and so on, and having the extension property. But this was all happening at the syntactic level, and then the model here was a model in the traditional sense, except it was not a model of the red theory T, but of each one of these pieces. Now here, one could say, well, what about using fourth systems, but for models? And here you can just, give you a definition. This is something extremely familiar, especially if you remember the description of the game we had from last time. So L is a logic, not a, it's a logic. So a fourth system P in the logic from a model M to a model N, or both are tau structures, there is no change in the tau now, is a collection of L elementary embeddings. So this is, the usual fourth systems would be like for first order, or even for, you can take atomic fragment of first order or something like that. But now you allow yourselves to change the logic and to use any logic you want. And now the fourth property is like we had before. The empty set, the empty function is part of the fourth system. And if there is some function in the fourth system and some point, and here it is in M. So there's again this asymmetry. It goes from the left to the right. Then there is G extending F in the fourth system. So it's another elementary embedding for the logic that captures A in the domain. So remember our games. So we had much more complication in our games from the slide for the first slide. Let me go. Yeah. I don't know why this is moving this way, but these games that we had here, they had a lot more complication than the ones we now have. But the fourth system here, one can ask, what happens if you look at these games, like the Cartagena game or the SHELAH game, but only in a one-way direction? One can do that, and that's one way of doing that. And the question I have is the following. Let me go back to where we were. We were at the end of this picture. I don't know why. Okay, great. Sorry. Something is going on here with this. Oh, okay, now it is fine. So anyway, so this turns out to be equivalent by a very classical, almost like folklore kind of a knowledge, to playing the classical in Voigt-Frise game, but with the anti-isomorphism player picking only challenges from the left. And so that part is, I think, quite clear. So this gives rise to the following idea. So the four authors use this to get, actually they use this because they're interested in Lowenheim-Skolimtarski style characterizations of the virtual cardinals. Those also have a history going back to Maggie Dorr's work and other people, Malitz and perhaps Shelah in the 1970s, working around Lowenheim-Skolimtarski characterizations of large cardinals. So now they want to do them for virtual large cardinals. And then their theorem is that the existence of a virtual elementary embedding turns out to be from from M into N, where M and N are now, in principle, arbitrary models. Of course, they will apply it to models of the form V alpha, V beta, but we can apply it for arbitrary models and see what happens. That is equivalent to the existence of a fourth system from M to N, or that N satisfies the virtualized logic theory of M. I failed to, to include here the virtualized logic, but it is essentially a closure of the logic under existential constructions corresponding to the existential property described in the fourth system, or that ISO has a winning strategy in the half, or in the half game or the virtual game. So that's, they characterize the existence of a virtual elementary embedding, and that's, I think, a nice thing to try. So let us see a direction that I want to blend with this. Let us go back to.
Sorry, I just wanted to say, historically speaking, the idea of using the fourth games to get virtual elementary embeddings and vice versa was Ralph's.
Okay. So
yeah,
oh, that's right. Yes. Sorry. Yeah. I should have mentioned. Yeah. That's correct, and that gave a lot of simplicity to the original definition of remarkable cardinals that was so difficult to deal with. Thank you very much, Pika. Anyway, okay. So what do we have now? We have these logics. We have all these musings between, fourth systems and maybe virtual elementary embeddings that you want to get between models or between, strata of the hierarchy. But let us remind ourselves of a, L1 kappa. And let's look at this blend that is happening now. But this is really, I'm just quoting from SHELAH 1101 paper, I think. So what happens if you allow, so if you do the same definition of L1 kappa that we described, last time and in the beginning today, but now kappa is theta, and theta is a strongly compact cardinal. So L1 theta. So, the somehow, when you use this notation, the notation L1 theta, we kind of assume always that theta is strongly compact. Now, this gives an interesting blend, and he has been able, SHELAH has been able to extract a lot of interesting model theory from the blend of the definition of L1 kappa, when kappa is this theta, under the additional assumption that theta is a strongly compact cardinal. I just described two things. He has a kind of Kizler-SHELAH theorem so it means that two models are L1 theta elementarily equivalent in the sense of that, that closure of those properties that we, described, that I described last time for you, if and only if they have isomorphic, not ultrapowers, but iterated ultrapowers. You have to do the iteration omega many times of the ultrapowers in a kind of more controlled way. That turns out to be, for those of you who are familiar with Malyaris's work with SHELAH on, the control you have by paying close attention to the sort of properties the ultrafilters you take the ultrapower with have. Well, that turns out to be part of that picture. It's a very beautiful line, I believe. And then there is also the role of special models. Essentially, let me just describe them here: unions of omega chains of iterated ultrapowers. I know this is not the usual definition, but this is the definition that ends up being really useful there. And then those are unique. Showing uniqueness of special models is a kind of exercise in first order model theory. And they are a good replacement for saturated models when you don't, when you cannot really guarantee saturated models in some cardinalities. Dealing with special models is usually very, very, very convenient and very useful. But now, if you take another logic, who knows? Who knows whether the logic has enough tools to show uniqueness of special models? And in this one here, there is a proof of uniqueness of special models in some cardinality. So the idea is you start at theta, you go up to some lambda that is cofinality omega, but you take its strong limit. So like a fixed point of the beta function above theta or something like that. And then you start iterating ultrapowers. You take the limit of that omega many times, and that's a very interesting model. It has uniqueness properties, so it's categorical for those models, so to speak. And that gives you easier proofs of the Craig property, the interpolation property, much easier than the ones without the compactness. And then you can blend it, because you have compactness, you can blend, you first prove Robinson, which is like proving disjoint amalgamation. You prove that for those special models, and that's enough to get the Craig property. This is just mentioned as an aside because I sense it has a connection with the other things that I am saying here, but I just leave it open at the moment. And I mentioned finally that there is a beginning of stability theory, and quite rich stability theory for L1 theta. But let me just close this musing that, by just pointing out again to the connections of the methods of Malyaris and SHELAH's constructions and what happens here. And there is also an extremely careful use of saturation, of how you slowly saturate models, that has a flavor that is not so different from fourth models that we already discussed. So that's one line. Another line would be, what about virtualizing L1 kappa? Oh, here I put L1 comma kappa in the title. It's L1 kappa, and then that's a typo. But so I see that there are at least two competing virtualizations of these logics, and they're not necessarily the same. First of all, one could just use the definition from the four authors, or from from Schindler, and with the difficulty of not having a good grasp of elementary embeddings, because remember, in the virtualization, you need in the game, in the fourth system, you need to have a grasp of elementary embedding, and that's exactly what's, I wouldn't say missing, but it is sort of difficult to keep track of in the SHELAH logic. It is better in the Cartagena logic that has, it's kind of closer to this. Or else, as I pointed out a few minutes ago, one could try to use a virtualized version of the SHELAH game. But by this I mean, just take the same game that we described last time and at the beginning of today. So not the Ehrenfeucht-Freysse classical game in virtualized form, as the authors here and Schindler do, but the SHELAH game or the Cartagena game. And again, here I think I somehow forgot to put the upper scripts and lower scripts here. This is Cartagena game beta C and then lower script theta. Anyway, so these games are exactly like in the original game, except only going in the fourth direction. So it's like you go to the original picture of the game that we had, like here, for instance. Okay. Okay. You look at this game, the SHELAH game, or you can imagine playing exactly the same game, but putting all the red challenges, A0, A1, A2, and so on the left-hand side, and see what do you get. And this is, I think, this gives an interesting kind of fourth system that is different from the one in the paper. And it also gives an interesting forcing notion as well as this. At the moment, I have no idea what properties do these forcing notions associated to those games have. Sorry, this kind of new work. But anyway, so we have both virtualized versions, and they're all essentially existential closures of the logics, but in a kind of weak second order existential closures of the logics. So they would give rise to two competing notions of virtual embeddings. Which one? Again, a question that I don't purport to answer now, but that might be of interest to some of you. Now, let me call a cardinal delayable, and the delay is because of the delay in the game. If it is a compactness cardinal for the second order version of SHELAH's logic, and I call it L2 kappa. Maybe it's not the best name, and I think there is also, it has been used in different ways, but I will call it for now L2 kappa. So it's like L2 kappa kappa, but now for L1 kappa. So it is a virtually delayable cardinal if it is a pseudo compactness cardinal. So remember, that was, instead of locally satisfiable models get a model, they get a pseudo model for the same logic. Now, if we replace that logic L2 kappa by the second order version of the Cartagena logic, then you get the corresponding two notions of card or Cartagena delayable cardinal and virtually card delayable cardinal. Where are these cardinals located? What kind of reflection properties do they capture? I think it'd be interesting to know, and I have some kind of sense of where they would be located, but I think both, I mean, if they coincide with other virtual large cardinals that are already defined in a different way, that'll be interesting, because then you get an alternate definition, or you get some similarity between the logics that is not in their definition. But you can also get actually new small large cardinals that might actually be connected to some other things. And then, of course, what kind of reflection properties do they capture? But the deeper issue beyond, because those are very specific questions that one could say, well, just work a little bit on the, and try to calibrate, and that's nice enough. But there is a deeper issue, which is what kind of virtuality do they actually correspond to? What version of fourth systems do they actually correspond to? So I just give the name of these large cardinals. I don't know if they're interested at all, or if they already exist under some other name. Maybe somebody here sees that clearly. But I close now with final reflections that come from a conversation with Javier Caicedo, who is somebody who has, thought a lot about fourth systems for different reasons. So we have here 5 notions: fourth systems, intuitionistic logic in general, forcing for sheaves, morphisms of sheaves and pseudo-models, and then the connection between virtuality and forcing. And this is kind of a long, extended discussion we have had with him over the years. He was my master's thesis advisor here in Bogota before I went to work with Kunin in large cardinals and in models of set theory in the US and before. And in a way, there is a conversation that somehow was brought back to life by the paper. He was very excited about the paper, the 4-author paper. He says there are very deep ideas there, and he sees different. What he sees is not what I see, of course, but this creates this sort of a conversation. So all of these notions seem to appear in different places, and in BDGM, of course, but in some sense also there is a paper by Caicedo and Sette from the 1990s, I think, linguistic sheaves, and they also have fourth systems used for different reasons. And the notion of a pseudo model from here seems to be a powerful way way beyond its use in the characterization of virtually extendable cardinals. Let me just quote something from his email message that I think is interesting. Yes. There is a connection with model theory that I think is interesting here. I'm just translating ad libitum from Spanish, so I see a great novelty. The applications look quite impressive in the use of fourth systems for vocabularies, like the ones we saw, as in the definition of pseudo-models. That's something I don't quite understand at the moment, but that looks quite natural in the context of second-order infinitary logic, because they provide exactly the sort of extension property for vocabularies that guarantees satisfaction or forcing of second-order existentials. Now, he compares it in some other part of his message with the role of saturation. He says many times we do exactly the same thing in model theory, in traditional model theory, but not using forcing, but using saturation. And anyway, this is part of this conversation that I want to engage and hopefully continue with anyone here who might be interested in this. So thank you very much. This was a short lecture, but I think this was, part of the idea. So thank you again. Gracias de nuevo. And I leave with you with this painting by Chilean painter MATTA, The Integral of Silence. Thank you very much.
Andreas, thanks very much. It was actually really interesting to see your view on these ideas that we're still sorting out. And I might have to steal that image you have on pseudo models for my slides.
Sure. Yeah. I can send you all of these, of course. I will send you this lecture. There was an appendix to the lecture because all of this is connected to abstract elementary classes, but I don't want to go into that now. At some more point, maybe. But yeah, of course, I will send you this, and please, use it. And of course, if if continuing somehow part of the conversation was part of the idea of this second presentation. It was very different from the first presentation, which was, work that had been already done either by SHELAH or by myself and Yoko. Here it is more, okay, how can you connect all these ideas? I know it is an unusual format for a lecture, for a seminar lecture, but I hope it will provide some conversation.
Okay, so I have a small question and a comment, but if anyone has questions first, let's just do that. So does anyone have questions?
I had a small comment, maybe. So Andres, you asked whether the strongly unfoldable cardinals are in a sense virtual large cardinals. And I think in a way, I have a positive answer for that.
Really?
But yeah, but it's you know, positive in some sense. So you know, these there's this hierarchy of reflecting cardinals that were introduced by Miyamoto. That kind of, they don't exactly characterize, but they are connected somehow to levels of forcing axioms. So he has this notion of a plus. I don't remember. Yeah, he said something like he defined lambda reflecting. The kappa is lambda reflecting, and that then allows you to force you know, a level of the proper forcing axiom, not the full one, but basically the one up to level lambda. And if you look at the virtualized versions of these forcing axioms, there's a corresponding hierarchy of what I call remarkably reflecting cardinals. So these are all virtual. They are, so to speak, so you can stratify the whole region from a reflecting cardinal to a fully remarkable cardinal into levels, and these are the remarkably reflecting cardinals. And the strongly unfoldable cardinals are at the level, at the second level from the bottom of that hierarchy. And the funny thing is that, so they are in a sense a level of a virtual, of a hierarchy of virtual large cardinals that goes from reflecting to remarkable. But the funny thing is that there is no so you have these two hierarchies of reflecting cardinals, the actual one and the virtual one, and they kind of separate at the level after the strongly unfoldables. So the strongly unfoldable cardinals both are on this hierarchy leading up to the remarkable cardinals, and also on the one leading up to the reflecting the fully reflecting cardinals. So in a way, they can be viewed as a level of a hierarchy of virtual large cardinals, but they have an equivalent characterization that does not talk about virtuality. The distinction only shows up later.
That's really interesting because in a way, yeah, I mean, at some point, Philip Welch became quite interested in extracting a lot of connections between strongly unfoldable cardinals and class forcing properties, you know, connected to the sort of kind of, well, maybe in retrospect, it was connected to what Schindler did with remarkable cardinals, but this became extremely technical very soon. Well, just look at the definition of remarkable cardinals, and then that, you know, that maybe, you know, that they somehow are this split where somehow the virtual and the non-virtual are still kind of the same, and then
yes, exactly. That happens with, yeah, but both with the hierarchy of forcing. So there are these bounded forcing axioms, right? That kind of lead up to the full forcing axioms, and yeah, if you look at the totally bounded forcing axiom, it's the same whether you consider the virtual version or not. And also one step higher, there's no distinction. But at the level after that, they are very different. I mean, consistency, strength-wise, and everything, they are very different. And yeah, and so somehow I think you can, in a way, I feel like the strongly unfoldables are at the level where the bifurcation happens. So you can both view them as being on the level of, on the hierarchy of virtual large cardinals and also on the other one. That's how, yeah, I have a paper about that where I introduced them.
Yeah, I was going to ask actually, Gunther, whether this was written up somewhere.
Yeah, I have written that up.
Okay, great. Can you send it to me?
Sure, yeah.
Okay, perfect.
Well, this is wonderful. This is, you know, I'm learning a lot of things about strongly unfoldable cardinals by listening to what you are saying. And, you know, this is amazing. And you know, the origin of those cardinals was not looking for large cardinals per se. Of course, it was more trying to understand how some theorems on chains, elementary extensions of models of a model theory could somehow be made similar to what happens in models of arithmetic in works, you know, like those that you see in the MOPA seminar, perhaps more often, you know, like Schmerl and Cossack and Ayat. And I was very inspired by, so there were no large cardinals in Ayat's work at all, but I was trying to mimic what was the little that is known about model theory of arithmetic. I mean, a lot is known, but the little compared to the sort of model theory one would want. People usually say, well, there is no model theory of, things like ZFC or piano arithmetic. But then you look at Schmerl's and Kozak's book, and well, there is a lot, but it's done in a different way. Some parts are, as I have come to realize later, some parts have a lot to do with some of the techniques that are now appearing in model theory, in more mainstream model theory around NIP classes, but that's another story. So many of these questions actually led to the definition of those cardinals. And that point, in the thesis, I had to, prove things about these, like how they interact with forcing and all these things that were, that are well known by you, but I wonder how this split that you describe has to say about the original questions that led to their, definition of those cardinals. Mm-hmm. It might have, because it has a flavor of something going on with these models of set theory when you try to look at their properties in connection to models of arithmetic. But
yeah, that's a very interesting question. Yeah, I mean, it's true. The version of, I mean, so there's this alternative definition of strongly unfoldable that, I mean, I guess Miyamoto defined this and then showed that it's equivalent to your definition of strongly unfoldable. And the version he formulated is the one that I extended. I mean, that you can put into this virtual hierarchy. But it would be interesting to see what happens if you stick with your original definition, if there's a way to do that too. I'm not sure. I had never thought about that, I have to admit. Yeah.
Well, I have to look at your paper, definitely. I mean, sorry, I kind of, started wandering to in different directions, and it's been a long time since I thought about these issues. So, yeah. Thank you very much. Mm-hmm. This is wonderful. So, and thanks.
Yeah, I have a kind of question. Classically, I mean, I'm thinking of Bob Vaught making this remark years ago that we do, I mean, this game that we're playing back then, to define large cardinals, you take a property of omega, like the compactness of the ordinary logic, and you assign that property to big ordinal and call it, and now you have a new large cardinal. And, but you see, and your work seems to be reversing the game, and some that you're taking these large cardinals and you're sort of creating logics. And you're creating very abstract logics, which are defined by means of games and things. Completely, Yeah. Now, is there any way of collapsing that, like via the Ehrenfreund-Freisey games or something, collapsing that back onto omega? Some of these logical ideas you've created at a very high level.
I somehow so the original logics, the ones where I started today and a week ago, they don't really have large cardinal flavor, or implications per se. It's only today that we start, I started kind of blending them with compactness properties, or at least 2 or 3 different kinds. But having said that, there's always a question of how can you pull down to omega versus finite some of the situations that are happening there? Of course, the first answer would be, well, if you're looking at strong compactness properties, of course, there is it kind of collapses when you go down to omega. But I think you're looking for a more fine-grained answer than that, like especially when you mentioned the Ehrenfreund-Freisey game, and when you ask about like more finitary versions of the game that is happening here, and that's a I've been thinking about what does this have to say about finite objects in some sense. Now notice the first thing to say, I said last time, not today, is that the game itself is finite. In spite of the fact that you have all these cardinalities and ordinal clocks and all these infinities going on, the game's length is finite. And that makes it much more, approachable. Of course, it is finite because of the descending chain of ordinals. And in spite of being finite, you have a lot of things to play with the ordinal clock and with the structure of the ordinals happening. And I wonder how well does that reflect. Let me just mention that people who look at models of arithmetic have ways that are, in the MOPA seminar, these are discussed quite a lot, where you essentially start looking at omega a little bit like a large cardinal by looking at like chains of models that are finite but so long that you can model Paris-Harrington phenomena or things that are outside of what you can prove directly from piano arithmetic, even though they happen in the finite world. There is a method called the LN models that was invented by SHELAH in the 1980s to deal with what would be forcing for arithmetic in a way. Then it had been completely forgotten, and then Corey Switzer, started, proving things using that method. And a student of mine, David Valderrama, is now finishing a master's thesis, kind of generalizing some of these ideas. And he has found some problems with the original paper of SHELAH that are, as you can expect, difficult to deal with. This is the person who called a moment ago, by the way, because this is the last day he has to, to submit his dissertation. And there are lots of similarities, and large cardinal-like phenomena start appearing there. And it is somehow connected with, also Harvey Friedman's connections between models of arithmetic and large cardinals. They are all kind of there. So I wonder if these specific games that we were describing have, some version there. I'm just, thinking aloud. Sorry, I'm just, I don't have a good answer for your question. But
you're doing a kind of reminds me of algebraic logic. You're trying to do logic without syntax at times up there, right? And
yeah. That's I didn't. Yeah. So in a way, that's yeah. So yeah, that also has a because there is this SHELAH logic that also has no syntax or very weak syntax, and that is close to logics that have better syntax. Yeah. But I don't know algebraic logic very much.
I had a question about virtual cardinals. And do you in which forcing extension does the embedding lie? Like, does that have anything to do with like definition, or does the forcing have anything to do with like extendable cardinals, or like, do you ever say anything about which forcing extension the embedding lies with the virtual cardinal?
Well, this is really a question for Vika, and but let me just say quickly that normally you can capture these extensions with a collapse of cardinals forcings. So even if it lives somewhere else, there are ways of making it more canonical. In the description I gave here, I just said, well, there's some set forcing extension, but there are ways of capturing it. I think in the paper, Vika and the three other authors, they actually used quite carefully in it, but this is something I'm not really qualified to answer beyond this point. So maybe Vika has something to add about this.
So Aaron, actually there are these absoluteness results where if you have an embedding, say from J from V alpha to V beta in some forcing extension, you already have it in the collapse extension where you just make V alpha, which is the source of the embedding, have size omega. So all of them exist in collapse extensions, sort of the simplest extensions, the simplest forcing extensions that you can think of. You just take the domain of the embedding and you make it countable, and then you have it there.
And so if it wasn't another forcing extension, it would have already been in the one you described.
Exactly.
And so then there's no like virtual like I mean,
Exactly. Yeah.
Okay.
So the forcing extensions are in some sense extremely simple and also very, very bad because you've made the object that you're working with countable.
mm,
Yeah, in a sense, I would say, right, the forcing is simple in the sense that it's easily definable, but it's very complicated in the sense that it absorbs any other forcing that, you know,
True,
of that size.
That's
So
true. Yeah, and this is why the absoluteness theorem works in the first place. Yeah, that's true.
thank you. It's just a really interesting topic. So thanks.
Yeah, thank you. Thank you all.
I wanted to just toss in another path to follow. Maybe people know about it, but SHELAH has this notion of a beautiful cardinal, which it turns out is the first omega Erdos cardinal. And he uses it to simplify the classification, the main gap, that things either well, I don't know if I need to explain that. It's just too dead. So he has this. He has another use of this cardinal, which now appears to be something that might be virtual, and so maybe people would like to explore that.
That's a very interesting thought. I had not at all made the connection with beautiful cardinals, and they seem to have. I don't even know if they have a definition with embeddings.
What is that definition approximately?
Sorry?
What is the definition?
Just a second.
Vaguely?
Well, so the definition. Let me just see. I wrote this up in a survey of this fall. So.
Yeah, I don't remember. I'm sorry.
I'm trying to think. I mean, it is in fact. Yeah, SHELAH's notion of beautiful cardinal was characterized earlier as the least Erdos cardinal.
Is the
And I mean, I think what this means is that Solomon came on the notion. I'm just trying to see. I mean, basically, I don't know. I don't think I actually have the combinatorial definition now, but the purpose of it was to get a Nash-Williams theorem for cardinals beyond omega 1, and in particular for a beautiful cardinal is one where you get a kind of a good notion of well quasi-ordering on such a cardinal.
I don't know. But maybe, there is a notion of forcing isomorphism that is also, you force the isomorphism essentially by treating the back and forth system as a forcing, and then in the extension that becomes an isomorphism. But the isomorphism was not there in the model to begin with. And the main gap classification is known to be connected to forcing isomorphism properties of theories, at least for first order. But this is a line that I only know I was reminded of it by your question, because now it will be more about forcing embedding, not embeddability, not isomorphism.
Well, that is probably relevant here, because the crux of his simplification is that instead of counting isomorphism, he's counting bi-embeddability classes.
Oh, okay.
And he shows that what he gets is that the issue was that you look at the main gap, and on the one hand you have these model theoretic properties which are absolute, and on the other hand you're saying here's a whole list of spectrum functions which are very much not absolute. Right? You change the cardinal arithmetic and you've changed the spectrum. And he felt that was unsatisfactory, and so he got a definition that so he got a theorem that says either you're going to have the number of models, the number of maximal models will, the number of mutually non-embeddable models can be everything, as if you're in the bad case, can be everything up to the first measurable, but up to the first beautiful cardinal, and can't be that big.
Okay. Yeah. I don't know.
That's really interesting.
Yeah, there seems to be another web of connections
Mhm.
underlying that. Yeah.
Well, so
Very-
there's a paper on my website called, what is it called? The Dividing Line Methodology, Model Theory, Motivating Set Theory. And there's a page and a half, which is a quick survey of this result.
Okay.
The battery was about to die.
Okay. Are there any more questions? This is a case where the discussion session could get longer than the talk.
Yeah. Yeah, the talk was not that long. But yeah.
We would still have some time to go.
When you're done recording, I have a non-related to the talk.
Okay, I mean, yeah, so are there any more questions? If not, then I will stop recording. Okay, I think we're done.